All right, hello Math 170. Sorry we couldn't meet in person today, but hopefully we'll be able to meet in person on Wednesday for the first time. In the meantime, we're going to cover a few different things today. So we're going to start out the video with a bit of an introduction to the class. We'll go over the syllabus briefly, and then I'll move into section 3.1, which is the first content section for the course. And when we meet on Wednesday, I will go right into section 3.2. So make sure that you're comfortable with all of the ideas that show up in the video. Maybe you don't have to watch everything necessarily. I have a bunch of different examples you can skip through if you want, but you should feel comfortable with all of the ideas that show up and maybe start on your homework before we meet in class on Wednesday. Okay, so let's get into some important information you should know for the class. So first off, just an overview of the topics we're going to cover. We're going to start out the semester talking about systems of linear equations. So that's going to be what we talk about in section 3.1 towards the end of the video. We're going to talk about row reduction of matrices, how we can use that to solve systems of linear equations. Chapter 4 is going to be about matrices, which some people have probably never seen before. But we'll talk about matrices just as a mathematical object, how we can add them, multiply them. We'll take their inverses, and then we're going to use them to talk about game theory in section 4.4 and eventually Markov systems way towards the end of the course in chapter 7. In chapter 5, we're going to talk about linear programming for a bit. Linear programming just means methods that we can use to maximize certain quantities that have constraints with linear equations. We'll talk about sets and set operations in Chapter 6, we'll also talk about counting techniques in Chapter 6. So this is where we're going to talk about permutations and combinations and so forth, things that maybe you've seen before in the past. And then finally in Chapter 7, we'll talk about probability and do a bunch of different things with probability. That'll be our whole third unit for our third midterm exam. All right, so here are the things that you should be doing in this class if you want to succeed. I can't guarantee that you're going to succeed, but I will tell you that if you do all of these 5 things that I have listed here and you don't pass the class, I would be very surprised. So the first thing you should do is show up to class. That's usually a good way to start your pathway to success. Secondly, do all of the homework problems that I assign you. Literally every single homework problem. Homework is kind of built into the class as a way to boost your grade. It shouldn't really be taking away from your grade. But if you don't do the homework, then the homework is going to take away from your grade, and it's going to be difficult for you to pass when your homework is dragging down your final grade. The next thing, I would say read the textbook when you can to fill in some information that maybe we don't cover in class. We have a limited amount of time in class, so I can't cover all of the examples that are showing up in the textbook, but there will be more examples that show up on the homework, and so if you get stuck, use the textbook to help. If you're struggling with some content, then please come to my office hours, which are listed in the syllabus, or send me an email. Either one would be fine. Or work in study groups with other people that are in the class. That's a good way to go as well. And then finally, this should kind of go without saying, all of the graded assignments, like quizzes and exams that we take in class, you need to make sure that you show up for all of them. As I'll say in a bit, I will drop your lowest exam grade and replace it with the final if that helps you, but you should still be showing up for all 3 of the midterms and the final, and all of the quizzes that we take. All right, so here are the things that you need for the class. You need the textbook, which is listed there. You need access to WebAssign. I have instructions to get into WebAssign posted on Blackboard and course content. And then you need a graphing calculator too. So the TI-84 is kind of the standard graphing calculator that's used in all kinds of different math classes, but I think any graphing calculator would probably be fine. It doesn't even have to be a TI graphing calculator, but anything that you have would be fine. If you don't own a graphing calculator, maybe you want to borrow it from somebody that you know if you don't necessarily want to buy it. But otherwise, you're going to have to buy one for the class. All right, so here are my course policies. Again, just attend class. There can be a penalty that's deducted if you don't attend class. So if you miss more than 10% of the classes, then I reserve the right to deduct 10% from your final grade. I will have an attendance sheet that I pass around class at the beginning of every class, and you're going to have to initial and sign in. Cell phones haven't been a problem for me in the past few semesters, but I have had problems before. So if they become a problem, then I just reserve the right to confiscate them if it's an issue. So hopefully it's not going to be an issue. Homework, I do allow you to submit homework late, but you have to let me know before the homework is due. And the penalty for late homework is 20% per day. And then quiz and exam makeup, again, you have to let me know like the day before or earlier, then the quiz or exam is going to take place, and then we can work out whether your excuse warrants you to make up the quiz or exam at some other time. But you need to let me know before the quiz or exam. You cannot let me know afterwards, or I won't let you make it up for any reason. All right, so here are some assignments that we're going through this semester. The homework, all of the homework is assigned through WebAssign, and typically I'm going to assign one homework assignment for each of the sections that we cover in class. So for example, today we're covering section 3.1. On Wednesday, we're covering section 3.2. So in WebAssign, you would have an assignment for both 3.1 and 3.2. But even if you have multiple assignments that are assigned in 1 week, all of the homework for that week is going to be due on Sunday night at 11:59 p.m. We have quizzes as well. So we have 9 different quizzes that I have listed in the course schedule, which is at the bottom of the syllabus. Quizzes are always going to cover the material from the previous week, and at the end of the semester, I'm going to drop whatever your lowest quiz grade is. And then we have 3 different midterm exams. All of those dates are also posted in the course schedule. So when you get done with this video, please do go to the syllabus and just, glance through it to make sure that you understand what's in there. Take a glance at the course schedule at the end so you understand where the quizzes and exams are expected to happen. And then finally, we have a final exam. And the final exam is cumulative, and it takes place on May 2nd at 4 p.m. in our classroom, Coliseum 1015, I think. And I will replace your lowest midterm grade with the final exam grade if it benefits you. And then finally, I haven't decided yet, but I might assign a few application assignments that you would hand in some paper with work for. There would be maybe 1 per exam, but if I do that, I'll let you know in the upcoming weeks. All right, here's your grading distribution here. So the grades are going to be determined with the following weighting. Homework is 15%, quizzes are 15%, each of the midterm exams is 15%, and then the final exam is going to be 25% of your final grade. And I will tell you up front that at the end of the semester, I'll take your final grade and I'll round it up by 0.5% if it helps you. So for example, a 79.5 becomes a B, an 89.5 becomes an A, but this cutoff is strict. So if you have a 79.4, you're going to end with a B+. I will not round it up. Okay, so then we're going to move over to section 3.1. Okay, so with the introduction out of the way, let's move on to section 3.1. So chapter 3 is all about taking systems of linear equations and manipulating them to find solutions if they have any, or maybe they'll have an infinite number. But this whole chapter is devoted to that question. And in section 3.1, we're going to start off with kind of the easiest non-trivial case. So this section is just about systems of 2 linear equations and 2 unknowns. And because we're starting out with a simple case, this should be something that you've seen before in an algebra class, probably in high school, or if you took Math 111 here, then maybe you saw it there as well. And then next section, we're going to take the ideas and generalize them to systems of linear equations and more variables, and to do that we're going to introduce matrices, which is something that's a little bit less common for people to have seen in high school, although it does happen sometimes. So next section we're going to probably go into some uncharted territory. But the goal of this chapter is to figure out if we have some system or collection of linear equations, is there some efficient method that we can use to find the solutions? That's the big question we want to answer. So I'm going to start off with a definition. If we're going to talk about these linear equations, then we might as well define what they are. So a linear equation in 2 variables is an equation of the following form. So it's an equation that looks like ax plus by is equal to c. And here x and y are the two variables inside of our equation, and a, b, and c are just any real numbers. So the important thing to note here is that a linear equation is an equation where the variables don't have any interesting exponents. So they're all just raised to the first power, x and y. So let's give some examples of some different linear equations. So one example might be 2x plus 3y is equal to 6. This is a linear equation. Another linear equation might be y equals 7x minus 2. And at first, if you're looking at the definition, you might say, wait, this doesn't seem to match the form that was given up here for a linear equation. But it is in that correct form as long as we reorganize the equation. So we can move x to the other side, and we get negative 7x plus y is equal to negative 2. And now it's in the right form. So as long as we can move it into the right form, it's still going to be a linear equation. And now an example of an equation that's not linear. Y minus x squared is equal to 0 would be an example of a nonlinear equation. And this is nonlinear because x is raised to some interesting exponent other than 1. In this case, it's squared. All right, so linear equations always have an infinite number of solutions. That means that there are an infinite number of ordered pairs, x and y, that we can plug into the equation to make the equation true. And the graph of a linear equation, at least in two variables, is always going to be a line. So if we move up to more variables than just two, in the case that we're working in 3 dimensions, for example, we would have a plane as opposed to a line. But at least for this 2 variable case, whenever we would plot these in the Cartesian plane, we're going to end up with a line. All right, so let's move into our first example. Let's say we want to determine all of the solutions of the equation 3x minus 2y equals 12. So this is all of the ordered pairs that look like x, y, that I can plug into this equation to make the equation true. So we're going to start off by rewriting that equation given to us, 3x minus 2y equals 12, and solve for y. Okay, so first off, we can move 3x to the other side, and we get minus 2y is equal to minus 3x plus 12. And now we can divide both sides by a negative 2 to solve for y, and we get y is equal to 3/2 x minus 6. So now that we've rewritten it and solved for y, the variable y is a function of the variable x. So for any real number x that I plug into the right-hand side of the equation, I know that the y value is going to be 3/2 x minus 6, which means that the ordered pair that has the form x for the x component, and then 3/2 x minus 6 for the y component, this is always going to be a solution. Regardless of which real number x I pick, when I plug it into this ordered pair equation here, it's going to pop out a solution to the linear equation. So we call this tuple x and then 3/2 x minus 6 for y. We call this the general solution, because in some sense it encompasses all of the solutions to the linear equation here. We just plug in an x and it's going to give us a corresponding solution. And it's the general solution of the linear equation that we started with, 3x minus 2y equals 12. All right, but to get a particular solution, as opposed to a general solution, we can just take any value of x and plug it into the general solution. So I did 3 different examples here. We can look at what happens when we pick x equals 2. Then our general solution is going to turn into 2 and then 3/2 times 2 minus 6. And we can simplify this, and we get a 2 minus 3, I believe. If we pick x equals 3 instead and plug it into our general solution, this will give us a different particular solution. In that case, we get 3 and then 3/2 times 3 minus 6. And if you simplify this, you end up with 3 and then a negative 3/2 for the y. And then finally, let's see what happens if we put in a 0. We get a 0, and then the 3/2 x is just going to become a 0, so we have a minus 6 for the y. Okay, so when we write the general solution in this way, where we have x for the x component and then 3/2 x minus 6 for the y component, we would say that x is a parameter and the solution is parametrized by x. So the parameter with the general solution is going to be the value or the variable that's left inside of the general solution here. And it's called a parameter because as you adjust the parameter, you're going to get different solutions. So I can pick any value of x that I want, and a corresponding solution is going to pop out of the general solution. Okay, so we could have taken this linear equation that we started with, 3x minus 2y equals 12, and solved for x instead of solving for y. And if we did that, we would have ended up with a parameterization by y. So y would have been the parameter, and the general solution would have incorporated the variable y as opposed to the variable x. So a general solution, generally, parameterized by x is going to have a form like this. So we put x as the x component, and then the y component is going to be some expression in the variable x, some function in the variable x. And the general solution parameterized by y is going to have some function in y as the x component, and then just y as the y component. Okay, so let's do another example, finding the general solution and a parameterization. So this time, consider the linear equation 5x plus y equals 10. And we want to find the general solution parameterized by x, and then we're going to find the general solution parameterized by y and see how they differ from one another. So let's start off by finding the general solution parameterized by x. First, we're going to solve for y. So we take our linear equation and solve for y by moving 5x to the other side. And we get y equals minus 5x plus 10. And now we can just write down the general solution parameterized by x. So we're going to have x as the x component, and now we know y has to be equal to minus 5x plus 10. So this would be our parameterization and our general solution. And then we can find the parameterization by y instead. So again, we're taking 5x plus y equals 10. But if we want to parameterize by y, we're going to solve the equation for x instead. So we move y to the other side, and now solve for x by dividing by 5. And we get x is equal to negative 1/5 y plus 2. And so the general solution in this case, the x component is going to be this expression in the variable y. So we have negative 1/5 y plus 2. And now the y component is just going to be y in this case. Okay, so now that linear equations are introduced, we can move on to systems of linear equations. So generally, a collection of linear equations is called a system. That's the definition. And a system of linear equations can have any finite number of equations, but at least for this section, we're only looking at systems of 2 equations. So to solve a system of linear equations, we want to find all of the ordered pairs or tuples x, y that satisfy both of the linear equations at the same time. And there are a bunch of different methods that you can use to solve systems of linear equations, and especially in 2 variables, all of these different methods are relatively good. But we're going to find out that when we move up to more than 2 variables and arbitrary systems of linear equations, some of these methods are going to prove much more useful than other methods. So the first method we're going to talk about is solving a system graphically. So we want to find all the solutions of the system of equations given by x plus y is equal to 3, and then the other equation is x minus y is equal to 1. So again, we want to find all ordered pairs x, y that make both of these equations true at the same time. So the way that we can find the solution graphically is by taking both of our linear equations and graphing them with whatever computer system you want. So I got these two graphs here from Desmos, which is a free calculator and computer algebra system that you can get online, or you can put it into your graphing calculator, and that's what you're going to be doing during our exams and quizzes. So you want to get familiar with the graphing calculator and taking equations and graphing them generally. But in this case, we have the linear equation x plus y is equal to 3, and we can solve for y and get y is equal to 3 minus x. And then our other linear equation, x minus y is equal to 1, we can make that into y equals x minus 1, and then we can take both of these equations and plug it into a graphing calculator or into Desmos or whatever other computer algebra system you want to use. And then we want to read off the intersection point after we graph them, and the intersection point of the two lines is going to be the solution. So the intersection point is this point right here, and we can read off that that point is just the ordered pair 2, 1. So there is exactly one solution to this system because there's only one point at which these lines intersect, and it is the point 2, 1. So we solved our system of linear equations. All right, so the next method we're going to talk about is elimination. So this time we're looking at the system 3x minus 2y equals 6, and then the other equation is 2x minus 3y is equal to negative 6. So ultimately, the game plan for using the elimination method is to multiply the equations by constants that allow us to add them together or subtract them together in order to get rid of one of the variables. And then we can move down to equations in one less variable. So let's go through how this would work. In this case, we want to multiply our equations by constants so that we can add them and eliminate one of the variables. So what do I notice? I notice that I have a 3x minus 2y in the first equation, and I have a 2x minus 3y in the second equation. And I want to multiply the equations by constants so that the coefficient of x and the coefficient of x in the first equation and the coefficient of x in the second equation are equal to one another. So I notice I can multiply 3 by 2 to get 6, and I can multiply 2 by 3 to get 6 as well. So let's multiply the first equation by 2, and this will give us a 6x minus 4y, because remember you have to multiply each term in the equation, and then the 6 is going to become a 12. And in the second equation, I want to get a minus 6 so that when I add the two equations together, the x's are going to cancel with one another. So I'm going to multiply the 2 by a minus 3. We'll multiply the whole equation by a minus 3, and this is going to give us a minus 6x plus 9y is equal to 18. Okay, and now notice that we multiplied by constants so that when we add the 6x and the minus 6x together, we're going to get a 0x. So the x's are going to cancel. And now let's take the equations and add them together and see what happens. We take 6x minus 4y is equal to 12, and we're going to add the equation minus 6x plus 9y is equal to 18. And the x's are going to cancel, the y's are going to become 5y, and then the 12 plus 18 is going to give us a 30. So now we have the equation 5y is equal to 30, so we have one equation with only one unknown, and now we can just solve for y. So 5y is equal to 30 is going to give us y is equal to 6. So we just divide by 5 from both sides. And now we're going to take y equals 6 and plug it into the original equation. Either original equation is perfectly fine, and then solve for x. So I picked the equation 3x minus 2y equals 6. So we're going to come back through and plug in for y. So we get 3x minus 2 times 6 is equal to 6. This gives us 3x minus 12 is equal to 6, which gives us 3x is equal to 18, which gives us x is equal to 6. So the only solution to this system of equations is going to be the ordered pair 6, 6. Okay, next method is called the intersection method. So here we're going to solve the system x minus y equals 0 and x plus y is equal to -6. So to use this method, we're going to take both equations and solve both of them for y. So x minus y is equal to 0 is going to turn into just y is equal to x when we solve for y. And x plus y is equal to -6 is going to turn into y equals minus x minus 6. And now we're going to take the right-hand side of each of these equations here, so just the expressions in x, and we're going to set them equal to one another. So we have x is equal to minus x minus 6, and now we want to solve for x here. So x equals minus x minus 6 is going to become 2x equals minus 6. And to solve for x, we get x equals minus 3. So now we have the value for x, and we're going to take that value and plug it back into one of the original equations to find y. So we have x minus y is equal to 0. Now we plug in our value for x, which is -3. And we get minus y is equal to 3. So y is equal to -3 as well. So the only solution to this system of equations is the ordered pair -3, -3. Okay, and then finally, this is the last method that we can use to solve a system of equations. And this method is called substitution. This is kind of the most natural one. It's the one that I would probably use if you gave me a system of linear equations in 2 variables. But here we have the system x plus y equals 3 and x minus y is equal to 1. So we're going to start out by picking either of the equations and just solve for a variable. We can solve for x or we can solve for y. Usually I solve for y, force of habit. So x plus y equals 3 is going to become y equals 3 minus x. And now we can take 3 minus x and substitute it for y in the second equation. So the second equation, x minus y equals 1, is now going to become x minus 3 minus x equals 1. And now this is going to become x minus 3 plus x is equal to 1. So we get 2x minus 3 is equal to 1. Then 2x is equal to 4. And finally, x is equal to 2. And now we take that value, x equals 2, and we substitute it back into one of the original equations, and we solve for y. So I picked the equation x plus y equals 3. We take x equals 2 and plug it in. We get 2 plus y is equal to 3, which implies that y is equal to 1. So again, we have exactly one solution to this system of linear equations, and that solution is going to be the ordered pair 2, 1. So generally, out of the 4 methods that we just introduced, the first one, the graphical method, was the only method that wasn't algebraic. So we kind of had to draw a picture to figure out the solution. All the other 3 methods are algebraic. We don't need a picture. And generally, these algebraic methods are going to be better for various reasons. And also, in all of these examples, if you throw in decimals and fractions, they can get quite annoying, kind of computationally involved. You can make a lot of computational errors. And because decimals and fractions are annoying, generally we're going to attack these problems by just multiplying the equations by constants that get rid of all of the fractions right away before we do anything else. So here's an example of a problem that involves that idea as well. So here we want to solve the system 1/5 x plus 1/3 y is equal to 0. That's the first equation. And the second one is 0.2x plus 0.7 y is equal to 0.1. So I chose the elimination method because it's the method that's going to come up the most throughout the rest of the chapter. And we'll explain why that is in section 3.2. But first, we're going to get rid of all of the fractions that are showing up and the decimals as well. So in this first equation, x over 5 plus y over 3 is equal to 0. We can multiply by the least common multiple of 5 and 3, and that's going to get rid of all of our fractions. So I'm going to multiply by a 15, and this equation now becomes 3x plus 5y is equal to 0. And for the second equation, I want to get rid of all of these decimals, and one way to do that is just by multiplying by 10. So if we multiply by 10, then this becomes 2x plus 7y is equal to 1. So now we've taken our equations that were given to us, we've multiplied by constants, and we've rewritten them to get rid of all the fractions and all the decimals that are showing up. And now we want to use the elimination method. So I want to take each of the equations and multiply them by constants so that when I add them together, one of my variables is going to cancel out. So let's try and get rid of the variable x, and we end up with a situation that's very similar to the last one. So I'm going to take this first equation that has a 3x, and I'm going to multiply it by 2, and this is going to give me a 6x plus 10y is equal to 0. And now the second equation, I want the coefficient of x to become -6. So I'm going to multiply by a -3, and now I'm going to have a -6x minus 21y is equal to -3. And now we're going to add the equations together. So we have 6x plus 10y is equal to 0 as the first equation. We have -6x minus 21y is equal to -3 as the second equation. And now we're going to add them together, and I get a -11y is equal to -3. Okay, and this -11y is equal to -3. We can solve for y now, and we get y is equal to 3 over 11. Okay, so now that we have our value for y, we're going to pick one of the original equations, or in this case, one of the equations after we got rid of the fractions and the decimals. So this equation right here. And we're going to take 3 over 11 and plug it back in for y. And we get 3x plus 5 times 3 over 11 is equal to 0. That's the same as 3x plus 15 over 11 is equal to 0. So 3x is equal to minus 15 over 11, and now we divide both sides by 3, and we get x is equal to minus 5 over 11. So the solution in this case, and there is only one in this case, is going to be minus 5 over 11, 3 over 11. So anytime you're solving a system of linear equations, if you want, once you get the solution at the end of your method, you can check that your solution is correct by just plugging the solution back into the original equations and making sure that both of the equations are satisfied. And you can do that when we move on to systems of linear equations and more variables as well. Although the more equations you shove into the problem, the more tedious it's going to be to go back and check that your solutions are correct. Okay, and as I kind of said before, solving by elimination is going to be the preferred method for our class because the elimination method is the one that generalizes the best to systems of linear equations in more than two variables. Because at this point, you're probably thinking that elimination was the most complicated out of all the ones that we did for the two variable case, and that's kind of correct. It does seem to be a little bit more tedious. But when we move up to equations in more variables than two, elimination is definitely the best way to go. Okay, so all of the systems that we've seen so far have had exactly one solution, but that doesn't always happen. There are two other possibilities. Okay, so the first possibility is an inconsistent system. So an inconsistent system of equations is a system that has no solutions. So here's an example of an inconsistent system. We want to find solutions to the system x minus 3y equals 5 and minus 2x plus 6y equals 8. All right, so let's try and do this by elimination, as we've been doing so far. So the x minus 3y equals 5, we're going to multiply it by 2, because I want the 2x and the minus 2x to add together to cancel out the x variable. And we end up with the equation 2x minus 6y is equal to 10. Okay, and now let's take this equation and the second equation that's given to us and add them together to eliminate x. So 2x minus 6y equals 10, and we're going to add minus 2x plus 6y equals 8. And we see that we get a 0x and we get a 0y as well is equal to 18. So we end up with the equation 0 is equal to 18. The problem here is that obviously 0 is never equal to 18. So 0 equals 18 can never be true. So we say that this system has no solutions, because if it had a solution, it would require 0 to be equal to 18, and therefore the system is inconsistent. So generally, to show that a system of equations is inconsistent, it's always kind of going to end up having this this form here. So you're going to end up doing some elimination and figure out that 0 would be equal to some other non-zero constant. So 0 would be equal to c, where c is a non-zero constant. And if we end up at a spot where we're requiring 0 to be equal to something that's not 0, then we say, okay, that's absurd, this is a contradiction, so there can't be any solutions then. Okay, and if you took an inconsistent system of two linear equations and two variables and you graphed them, they would look like parallel lines, which is why we end up with no solutions. If you have two lines and they're parallel, then they never intersect. So you can't have a solution to that system of linear equations. All right, and then the other possibility, so far we've had one solution. Now inconsistent systems have no solutions. We can also have a system of linear equations that is quote-unquote redundant. And a system of linear equations is redundant if it has an infinite number of solutions. So here's an example of a redundant system. We want to find solutions to x plus y equals 2 and 2x plus 2y equals 4. So consider we start with this first equation, x plus y equals 2, and we can multiply by a negative 2 to get negative 2x minus 2y equals minus 4. And we're multiplying by negative 2 because I want the negative 2x and the positive 2x to add together and cancel. Now we add them. We get negative 2x minus 2y equals minus 4 plus 2x plus 2y is equal to 4. And now on the bottom, this time we get 0 is equal to 0. So it's very similar to the last case, except this time the constants that are on the right-hand side of the equation end up adding to 0 instead. So we get this unhelpful equation that's always true. 0 is equal to 0. And this is happening because, kind of in disguise, the first equation in the system and the second equation in the system are really the same thing. So if you put them into your graphing calculator, they would both give you the same line. So in other words, any solution to the first equation is also a solution to the second equation. So any tuple xy that happens to lie on the first line has to lie on the second line as well, because these two equations define the same line. Okay, so we find the general solution in this case, that we have an infinite number, by solving one of the equations for y. It doesn't matter which one we pick, but x plus y equals 2 is a little bit simpler. So we solve for y then, and we get y is equal to 2 minus x. And so now the general solution to that first equation, and therefore the whole system of equations, since both equations they define the same line, is going to be x 2 minus x. So there's our parameterization. In this case, we now have an infinite number of solutions, one solution for each possible value of x, as opposed to only one. Okay, so to sum up this last section, if we have two linear equations and two unknowns, there are exactly three possibilities for what the solution set can look like. So the most common one is that there is exactly one solution to the system of linear equations. But it can also happen that we have no solutions when the system is inconsistent, or we can have infinitely many solutions. When the system is redundant. And these are the only three possibilities. And if you want to convince yourself of that, we'll just think of the different ways that lines might intersect. So if two lines are going to intersect at a point, then they can only intersect at one point. Or you could have lines that don't intersect at all, parallel lines. Or you could have two lines that are really just the same, in which case you would have the infinitely many solutions. So you can't have a system of two linear equations and two unknowns that gives you two solutions, for example. That's not possible. Okay, so we're going to end the video by looking at a couple of different applications of the systems of linear equations. So anytime we're going to apply some mathematical concept to the real world, we first need to take the real world scenario and write it in terms of the math language that we've developed. So first, in this case, we're going to identify whatever the unknowns are in the scenario that's given to us. So what variables are there and what variables are we trying to solve for? And when we find those unknowns, we're going to give them names so that we can put them into linear equations. After that, we're going to use the information that's given to us inside of the problem statement to set up a couple of different equations. And in this case, we're going to be looking at equations with two variables. So we're going to need two different equations, linear equations, to set up our system. And then finally, once we have everything written in the math language, then we can apply the methods that we've talked about earlier in the video to solve those systems and then pop out whatever kind of information we wanted in the first place. So for this first example, let's say that you manage an ice cream factory, and the ice cream factory makes two different flavors. It makes creamy vanilla and continental mocha, which from now on I'm just going to call vanilla and mocha. So let's say that each quart of the vanilla ice cream has 2 eggs in it and it has 3 cups of cream in it. And each quart of mocha has 1 egg in it and 3 cups of cream. And let's also say that right now inside of your store you have 500 eggs in stock and you have 900 cups of cream in stock. And the question is, how many quarts of each flavor should you make so that you use all of the products that you have in stock? So we don't want any eggs and cream left over on the shelf that are going to spoil. We want to incorporate all of them into the ice cream that we're making today and hopefully selling. So this is kind of an interesting problem to solve, and it ends up being solved with a system of linear equations. So first off, what variables are we looking at? Well, the last line here says that I'm looking for quarts of each flavor that I want to make. So we have 2 different flavors. We have vanilla and we have mocha. So let's say that the quarts of vanilla ice cream, we're going to represent that with the variable x, and the quarts of mocha ice cream that we're producing, we're going to represent that with the variable y. Okay, and we have 500 eggs in stock, which means that we want to use 500 eggs when we're making all of this ice cream. And we're told that each quart of vanilla ice cream has 2 eggs, and each quart of mocha ice cream has 1 egg. And now we're going to use this information to give us an equation. So if I want the total number of eggs that I use as a relation of the quarts of vanilla that I produce and the quarts of mocha that I produce, well, I have 2 eggs times the number of quarts of vanilla that I produce. So 2 times x, and that's all of the eggs that I'm going to use for vanilla ice cream, plus the eggs that I'm going to use for the mocha ice cream. And the mocha ice cream, I'm going to produce y quarts of mocha, and for each quart I only get 1 egg. So I want 2x plus y to be equal to 500. So this is our first equation. And now to get the second equation, let's look at the cream. So we want to use a total of 900 cups of cream, because that's what we have in stock. And each quart of vanilla is going to use 3 cups, and each cup of mocha also uses 3 cups. So all this information is given to us. And now we want to write down an equation. Well, if I want the total number of cups of cream coming from the vanilla ice cream, I'm going to take 3 times the number of quarts of vanilla that I produce, so 3 times x. And if I want the total number of cups of cream coming from mocha, I also have 3 times the number of quarts of mocha I produce, which is y. And we want this to be equal to 900. So the hardest part of doing these application problems is taking the information that's given to you and figuring out what the linear equations are. But after we have these linear equations set up for us, now we can just use the math that we've talked about. So now we're going to use the elimination method. 2x plus y is equal to 500. This is going to turn into, let's multiply by 3 so that we can get a 3y in the first equation and a 3y in the second equation and subtract to get rid of the variable y. So we get a 6x plus 3y is equal to 1500. So this is our new equation, and now we're going to subtract. So we have 6x plus 3y is equal to 1500, and we subtract the equation 3x plus 3y is equal to 900. Okay, and 6x minus 3x gives us a 3x. 3y minus 3y cancels out. So we have 3x is equal to 600. And now we can take that equation and solve for x. And we get x is equal to 200. And now we want to take that value for x and plug it back into one of the original equations and solve for y. So I picked the equation 3x plus 3y equals 900. We'll plug 200 in for x. And we get 600 plus 3y is equal to 900. So 3y is equal to 300, and therefore y is equal to 100. So we want to make 200 quarts of vanilla because that's what our variable x represented, and we want to make 100 quarts of mocha because that's what our variable y represented. Okay, and now we're going to move on to the last example for the video. So in this example, let's say that in December of 2014, the Twitter stock decreased in value from $40 to $36 per share, and the Microsoft stock decreased from $48 to $45 per share. So if you invested a total of $22,400 in both stocks at the beginning of December in 2014, and at the end of December you sold them for $20,700, then can we figure out how many shares of each stock you must have bought at the beginning of December? All right, so what are unknowns here? Well, we want to figure out how many shares of the Twitter stock we bought and how many shares of the Microsoft stock we bought. So we're going to let X be shares of the Twitter stock, and we're going to let Y be shares of Microsoft. Okay, so we can use the value of our investments at the beginning of the month to get one linear equation, and then we're going to use the value of our investments at the end of the month to get a different linear equation. So I know at the beginning of the month, if I take all of my Twitter shares and I take my Microsoft shares and I add their value together, I'm going to get $22,400 at the beginning of December. And if I take the number of shares that I have in Twitter and I want to find the value of all of those shares together, well, I'm going to multiply by the value of each share, which is $40. So the value of the Twitter shares at the beginning of the month is going to be 40 times X. And the value of the Microsoft shares at the beginning of the month is going to be 48, because that's the value of each share, times the number of Microsoft shares, which is Y, as I've defined it. So this is one linear equation that's given to us. And now the value at the end of the month gives us another linear equation. So I know that the value of all of my shares put together at the end of the month has to be $20,700, because that's given to us. And now the reasoning for the left-hand side of the equation is very similar, but this time we're going to use $36 for Twitter and $45 for Microsoft. So here we have 36 times x plus 45 times y is equal to 20,700. So now we have two linear equations and two unknowns, and now we can solve for both of the variables here. So first off, I noticed that both of the equations are kind of nasty. The numbers are just really big, but we can simplify them. So I started off by doing that. So this 40 and the 48 have a common factor of 8. So I'm just going to hopefully divide this entire equation by 8. And that gives us a 5x plus 6y. And 22,400 divided by 8 ends up being 2,800, a nice whole number. And the 36x and the 45y, well, they have a common factor of 9. So I'm going to divide that whole equation by 9. And I get a 4x plus 5y. And 20,700 divided by 9 ends up being 2,300. And so now these two equations here are a little bit nicer to work with. Again, we're going to use the elimination method because it's the method that we're going to use most. And the 5x plus 6y, I want to get rid of the x's, so I'm going to multiply by a 4 here. And this is going to give me a 20x plus 24y. And 2,800 times 4 is 11,200. And the 4x plus 5y, let's multiply this equation by 5 so that we can get another 20x. And we get a 20x plus 25y. And then 2,300 times 5 is 11,500. And now we're going to take these two equations and subtract to get rid of the x. So 20x plus 24y is equal to 11,200, and we're subtracting the equation 20x plus 25y is equal to 11,500. And so the 20x and the 20x are going to cancel, like we set it up. And then we have a minus y is equal to a minus 300. So we conclude that y has to be equal to 300. And now we're going to take that value for y and we substitute it, and then we solve for x. So I pick one of the equations up here. I picked 5x plus 6y equals 2,800, and we'll substitute 300 for y. So we get 5x plus 6 times 300 is equal to 2,800. So this is 5x plus 1,800 is equal to 2,800. And then 5x is equal to 1,000. And so x is equal to 200. So given the original problem statement, we must have bought 200 shares of Twitter, since Twitter was X, and we must have bought 300 shares of Microsoft, since Microsoft was Y. Okay, so you're going to have a lot more practice working on these application problems in the homework, but that is it for this video, and I will see you on Wednesday.